And finally, as we work with systems of equations, we're going to talk about the second algebraic method for solving systems, which is called elimination method. Now, the elimination method is an alternative to the substitution method. It works nicer in certain applications or certain problems, and other times the substitution method works better. And so it just kind of depends upon the problem, your preference. There are going to be times where I will specify which method you need to use, so I want you to get good at both of them. However, there are going to be certain times also where you get to choose, okay? So you'll want to know when to use each one, or at least be comfortable enough with both of them. Okay, so with the elimination method, the idea, again, just like in substitution method, you want to get the system down to one variable rather than two. So instead of having both x and y, you really want to have either x or y, okay? One way to do this is to add the two equations together. Now this seems kind of weird, but let me explain for just a moment the mathematical rationale as to why that works, okay? So think about this for a moment. There's a property in mathematics called the addition principle of equality. And it says that if you add something to one side of an equation, you have to add the same amount to the other side. And so here, what we're going to do is we're going to add, if we add the two equations together, essentially focus on the first equation as your sort of your fixed equation. The second equation, if I add 9 to the right side and I add x minus y to the left side, I'm really adding the same thing to both sides because those two things are equal to each other, okay? So I'm really satisfying the addition principle of equality. You can almost think of it as saying I'm adding 9 to the right and I'm adding 9 to the left, but the 9 I'm adding to the left looks different because it's just a different expression, but it's equal to 9. So it doesn't matter what it looks like. As long as it's equal to 9, I can add it to both sides, okay? And so that's essentially what happens. So if I add the two equations together, I'm adding, again, the same amount to both sides of the first equation, all right? That's essentially what's going on. That's why this works. So here, I'm going to go ahead and do that. If I add the two equations together, change the color up. I'm going to draw a line here, just, you know, how we put our summation, we add, put the total at the bottom. But I'm going to do this term by term, okay? So it's going to be combining like terms, essentially. So I'm going to get x plus x is 2x, y minus y is 0y. Now I don't really have to write that, I'm just doing it to show you, you know, that it's 0, just to show it there. And then 5 plus 9 is 14. Okay, well, in reality, that 0y doesn't really need to be there, so I'm going to write it as 2x equals 14. Again, you could just write this line and not write the line above it, that's okay. And then if I divide out the 2 to solve for x, I get an x value of 7. I can then take that 7, and remember, I don't have a final answer yet. I have to have the y value and then put them in the ordered pair form. So I take that 7, plug it back in. Now I can plug it back into either of the original equations. It won't matter. I'll go to the top one. We have 7 plus y equals 5, right? So the x becomes a 7. And then solve that for y very quickly. Subtract the 7 from both sides, and y must be a -2. And so I'm not quite done yet with this problem. Remember, once again, you must have a solution set for a system of equations, and the solution set will always contain an ordered pair. Must have the x first, followed by the y. Must have it in ordered pair notation with a set around it. Okay, so it's in a set. And so that's my solution set. So again, the elimination method works by, it's kind of a complicated way of doing the addition principle of equality. I'm adding the same amount to both sides of the equation, and what it does here is it eliminates one of the variables, okay, which is very nice. The y is dropped out. I end up with an equation with one variable, and I can solve that. The next example I'm going to show you is a little bit tougher because the variables don't drop out immediately. There's a little work you have to do. Sometimes you don't have a nice positive y and negative y to get them to drop out, okay? So let's look at another example where that's the case. Okay, this is one that we did in the previous video. So 2x minus 1 equals 5, and x plus 3y equals 6. Again, if I were to just add these straight up, nothing drops out. Oh, that's supposed to be a y. 2x minus, right? Yeah. 2x minus y equals 5. Sorry, I wrote that wrong. Okay, so again, nothing drops out immediately, right? 2x and x make 3x, negative y and 3y makes 2y. I don't get any zeros on those variables, so I need to do some tweaking to get that to work out. To make that happen, I want to get the coefficients on one of the variables to be opposites. And so I could choose to either go with the x's and make one of them a 2 and one a negative 2 somehow, or to go with the y's and make one a negative 3 and one a positive 3. Now, simply because I've got a negative and a positive already on the y's, I think that'll be a little bit simpler. Doesn't really matter though. But the question is, how do I make this negative y a negative 3y without changing the equation in some way that messes the solution up? And the answer to that is utilizing the multiplication principle of equality, where I multiply both sides of that top equation by 3. That would change the y to having a negative 3 coefficient without changing any of the solutions. It gives me an equivalent equation. So that's what I'm going to do. I'm going to multiply this top equation by 3, all right? So it essentially creates sort of a new system, and so I'm going to write that off to the side here. I would end up with 6x minus 3y equals 15. What you want to make sure to do is to multiply everything, all the terms, by that 3. Okay, so you're essentially multiplying both sides by the 3 and then distributing it on this left side. Then the bottom equation stays the same. I'm not going to change that one because it already has the opposite coefficient. So now I have a negative 3 and a positive 3. That's what I'm looking for. When I add these together, the 3's will drop off. So let's go ahead and do that. The x's become 7x. The 3's add up to 0. 15 and 6 make 21. And I divide out the 7. And I get x equal to 3. Now again, I'm not done. I've got to find the y value, so plug that x value of 3 back in. I'm going to go to the bottom equation. Again, it doesn't matter, but I think the arithmetic may be a little bit nicer there. So I get 3 plus 3y equals 6. Remember, the 3 goes in for x. And then I solve. I got to subtract the 3. 3y equals 3, divide by 3, and y equals 1. Okay, so again, my final answer must be a solution set containing the point 3, 1. Okay, all right. Now remember, this actually was a system we saw in a previous video where we did a substitution method and we got the same answer, so that worked out nicely. So that just kind of verifies to you that you can use either substitution or elimination method and you'll get the same answer. One thing I did want to mention, I'm just going to check something here in the book. Oh, you know what? The textbook, I just noticed this, doesn't use the word elimination, it uses the word addition. In some books, some authors, some teachers use addition method instead of elimination method. It doesn't really matter, but I might as well write it up here so that you know they mean the same thing. Okay, so the elimination or addition, depending upon who you're talking to, those are interchangeable. They are the same thing. Okay, now this example was nice because I only had to multiply one of the equations to get the coefficients to be opposite. Next example, I'm going to show you, you're not going to be able to get that easily. You're going to have to do both equations. Okay, so in this last example, you have 2x minus 5y equals 13, and we're going to have 5x plus 3y equals 17. Okay, so I've got this system, and again, my coefficients are not going to be able to become opposites very easily. All right, pretty obviously, you can't just multiply 2 by a whole number to get 5, or 5 to get 3, or you could work some fractions or decimals in there, but we're not going to try that. Instead, it's easier just to use whole numbers. So I'm going to multiply the top and bottom equations by different numbers to make one of the variables opposites. Again, I'm going to choose the y's because they already have opposite sign. Actually, you know what? Just because we did that on the last one, I'm going to go ahead and make this tougher. Let's go with the x's. They don't have opposite sign. There are times where you can't avoid this, so I'll make one of them positive, one of them negative. Let's go with the top one being negative. Now, because we have a 2 and a 5, I need to choose a least common multiple to turn them both into. In this case, I would choose 10, right? So I'll multiply the 2 by a 5 and the 5 by a 2. I'll make the top one negative so that they become opposite, not the same. So I'm going to do this in 2 different colors. The top one, I'm going to multiply by a negative 5, and the bottom one, 2 different colors, blue and green. Bottom one, I'm going to multiply by positive 2. Okay, so negative 5 on top, positive 2 on the bottom. When I do that, the negative 5 distributes to every term, and you've got to be very careful hitting every coefficient, every constant with that negative 5 and including the negative. So negative 5 times 2 is negative 10x. Negative 5 times negative 5 is positive 25. Why? Okay, so you've got to remember that negative. The negative 5 times the 13 is negative 65. And then we distribute the 2. 2 times 5 is 10. 2 times 3 is 6. And 2 times 17 is 34. Okay. From there, we add the 2 equations together. And like I said, one of the variables will drop out, in this case, the x's. X's add up to 0. The y's, we have 31 y's. And negative 65 added to 34 is going to be a negative 31, if I'm doing that right. Which works out nicely when I divide here. If I divide by 31, I get a negative 1 for my y value. Then I take that y value again. I've got to substitute it back in to find x. I can choose either of these equations. It won't matter. I'll just go with the bottom one here, just to save some room. 5x plus 3 times negative 1 equals 17. 3 times negative 1 is negative 3. I need to add the 3 to both sides. 5x equals 20. Divide by 5. And x is equal to, what's that, 4? Yes, x is equal to 4. So final answer, solution set, is the set containing the point 4, comma, negative 1. Right? So elimination method, again, the goal is to add the equations together in order to eliminate a variable like we did here. Sometimes you have to do some multiplication to the equations so that you can get the variable to drop out when you add them together. A couple of quick notes though. If you were to have a situation where both variables dropped out, then you're either going to have a no solution system or an infinite solution system. So let's say both variables dropped out. If both variables drop out and the other side is 0, then you would essentially have 0 equals 0, which is a true equation that leads you to an infinite number of solutions. If both variables drop out and the other side is not 0, like the other side ends up being 2 or something, or 31, then you have a false equation, 0 equals that other number, and that leads you to a no solution system. Okay, so those are two special cases. You will see that occur. I don't want to run through a full example just to save some time, but that's what happens. If the variables drop out, you end up with both variables gone. You're going to have one of those two situations depending upon what's on the other side. Okay.